Hello and welcome to this lecture on mechanical design. We will have an introduction to the course and discuss the various aspects that will be included and the topics and the scope, the grading scheme, and in particular the project where I'm going to kind of concentrate and discuss what is required. So the course is on designing high temperature components. So it's not a theoretical course where we will require a lot of mathematical calculations and mathematical derivations of the basic equations, but we will rely on your background in the strength of materials. So we need to know basic formulas for stress, such as bending, torsion, and tensile test, and stress concentration factors, and so forth. So basically, the prerequisite for the course is an undergraduate level knowledge in the strength of materials, where you have covered the formulas for mechanical components, stress and strain in mechanical components. The course is geared towards design applications at high temperatures, where we must confront the effects of both temperature and a mechanical load. So most of these applications, for example, turbine blades in jet engines, they have to be cooled because they are receiving a very high heat flux. And once they are cooled, the coolant itself is going to introduce a mechanical force, and the centrifugal motion of the blades will introduce an additional mechanical force. And also because there's going to be a heat flux from one side on the blade and the coolant on the other side, you get a temperature gradient. Once we have temperature gradients or differential thermal expansion, then we must also be worried about thermal stresses. So in short, the course is going to combine mechanical loading as well as thermal loading at high temperatures. And we'll define high temperatures as temperatures above half of the melting point, where the strength is reduced and compared to room temperature, and also time-dependent phenomena start to come in, such as creep, deformation over a long period of time, and such as cyclic fatigue due to the accumulation of plastic strain from cycle to cycle. And therefore, the course is, the core part of the course would be the applications of plasticity, both rate independent, which is instantaneous, and rate dependent, which is over a period of time, meaning creep deformation, as well as fracture type failure mechanism. So we will deal with these three topics mainly: plasticity, viscoplasticity, which is creep, and also fracture, where we will worry about crack propagation. So the way that we structure the course is that initially we will worry about material selection. We should know the properties of materials at different temperatures so that we can differentiate between one material and another. The bottom line is that the materials have different melting points, and for high temperature applications, we can select from very high temperature materials that have high melting point. However, because there are other requirements, for example, we must conduct heat, so the thermal conductivity is going to be important. We must also have adequate strength, so the yield strength and the mechanical properties will be important. We must have enough ductility. We also must have fracture resistance of the material. Not only that, but many of these materials are used under severe environments where coolants can cause corrosion and erosion. So in summary, material selection cannot be based only on the melting point, but it has to be based on a variety of other properties that we would study. And that would be the first part of the course. In the first week, we will learn about material selection, and then we will get in to discuss other topics that I will show you in a minute. So let's get started where we can look at the course content and what it entails. So you can see here that this is my class notes, which will be the textbook for the course. And the class notes are in the title, The Mechanical Design of High Temperature Components. An example you can see here where we have a jet engine, and the jet engine, the blue part that you could see here are the fan, it's like a fan blades that are on the cool side of the engine. So the fan will just circulate the air, and the air comes in at extremely high velocity, and the air will eventually go into the combustor. So there's a combustion zone here, provide the fuel, and it is mixed with the fuel, and the oxidation process leads to extremely high temperature and expansion of the hot gases, and hot gases will blow at high pressure and high velocity, high speed on the turbine blades that you can see on the right here that are glowing hot. And these blades are what we design in the course. So we design, this is an example of what would be objective of designing such components. So the course is not necessarily on a particular design of a jet engine, but it is for a wide range of components in mechanical design. So our objectives here are the topics. You can see material selection for high temperature applications. Once we selected the materials, then we would have a period of probably a week or so, week and a half, where we develop rheological models that describe the mechanical behavior of materials, meaning the relationship between the force and the displacement and the time. So these are the three elements where we would use simplified ideas to describe material behavior. These ideas will be a collection of elements like a mass, a spring, and a dashpot, the traditional elements that we used to have in physics, and we combine those to give us a simulation or a similarity to the complex material behavior that we would describe as stress-strain relationship or stress-strain time relationships that we use in finite element codes. Then the next subject that we will deal with is thermoelasticity and thermal stresses. And there we will deal with simplified components so that we don't get tangled up with a lot of mathematical developments of plasticity of complex systems. So here we would deal with the rods, beams that can be bent, and also tubes or cylinders that are pressurized from the inside or outside, axisymmetric systems where the thermal stresses can be analyzed rather quickly and with closed form solutions. Now, at the end of this period, I have also a little bit of exposition on the finite element method, because we will use it for simulation of multiphysics of design components. So for the finite element, we will write a MATLAB code that can solve a thermoelasticity problem in axisymmetric systems typical of many mechanical components, such as the combustion chamber of a rocket engine, or the cylinder used in car on the engine block of a car. So you will be able to practice that. The MATLAB code, we have it already, but we eliminate many statements to allow you to introduce yours and also learn by mimicking what we have in that code. The next topic is going to be plasticity. So we'll spend like a couple of weeks on plastic deformation, relationship between stress and strain, beyond the elastic limit, and using concepts like equivalent stress, von Mises stress, equivalent strain, and several models for hardening of the material, and just show how problems can be solved with this approach. We will focus on what we call limit analysis, where we would be able to develop closed form solutions for problems that can be described as elastic, perfectly plastic, where there's no hardening, and it gives us analytical solutions, bending, for example, or stretching of a rod. Next topic will be on viscoplasticity, and that is the time-dependent phenomenon, or creep and creep deformation. The key feature of creep deformation is that if you have a cylinder or a tube in a heat exchanger, for example, that has a pressure from the inside, operating at high temperature, it will deform slowly over time and will stretch and elongate and increase in diameter. So under these conditions, the shape will change. So creep is described by large deformation. So large deformation mechanics. So we will use this idea to find a couple of solutions to large deformation of tubes in particular. So we'll focus on tubes. And the last topic that we have would be on fracture, and we will not give a course on fracture mechanics, but we have the basic formulas that are used in a design setting, design applications, to utilize what we know as the J-integral approach, stress intensity factors, failure assessment diagrams for design, and that will conclude the main course topics. As I mentioned, the textbook, one is my class notes, which I'm going through here to show you on the screen. And then there's a reference that some of you may find interesting or important if your field of study is mechanics, for example. You might want to have a look at this book written by Lemaitre and Chaboche, and the title is Mechanics of Solid Materials. It's a little bit advanced course, advanced topic here in the reference, and therefore it's not required in my course, but it is for those who want to go a little bit curiosity beyond the course material. Now I talk about grading, so let me switch to the grading idea. The grading is that I have a homework assignments. We have 6 homework assignments that constitute 10% of the grade. This is also added to a midterm exam, and the midterm exam is 20% of the grade. And for the midterm, we will be allowed to use 2 cheat sheets, each one like maybe two sides of one single 8.5 by 11 page, where you can summarize the basic equations needed, and then you can use it in the midterm exam. The project has a substantial component of the course grade is 40%, and we will do the project in teams of 2 to 3 students. You can team up with the students. If you're online, then you can team with other members of the online class, and or you can team up with other students who are taking the course on campus at the same time. For example, in this lectures for the fall 2019. We have offering the class on campus at the same time online, so you could also look for people who can team up with you. And the final exam has 30%, and it will be open notes, where you can bring in either a PDF version of the notes or a printed version of these notes. So this is basically showing you the course grading policy. And now I'm going to just show you the contents of the course quickly as we see it here, to talk a few words about each subject. So the subject, you find chapter 1, material selection, and understanding modes of failure, and differentiating between different alloy systems, aluminum alloys, steels, titanium, nickel-based superalloys, insulating materials, and ceramic matrix composites. So each class of these materials that are used at high temperatures, we will show you their properties, how the properties vary with temperature, how does the yield strength vary, how does the ultimate strength vary, and so on. Then we use an idea of material selection using what's known as Ashby charts. And an Ashby chart is a chart between, it's a relationship between two properties, one on the x-axis, one on the y-axis, and this relationship is used for particular applications. For example, if I'm interested in classifying materials related to their thermal shock resistance, then I would have two properties that can describe the thermal shock resistance. And from there, I can group the materials in bubbles on that chart. And each bubble will tell me the relative resistance of the materials within related to thermal shock, and so on. So there's many different properties that we will do that. Diffusivity, conductivity, diffusivity chart, conductivity thermal expansion chart for strain mismatch, and so on. So that's the first chapter. Second chapter, rheological models of mechanical behavior. And that goes through the various standard tests. We know all about the tensile test, but there's more to it. And that's a hardening test, a creep test, relaxation test, cyclic test. So all of these are discussed. And from there, we discuss descriptions of material behavior. And these descriptions are sometimes used in finite element codes or in discussions between designers. Things like perfectly elastic solids, viscoelastic solids, elastic perfectly placid solids, elastic hardening solid, and so on. There's a variety of those that we will describe and define. And not only that, but the behavior is going to be represented mathematically by simple model. And the simple models, we have a Maxwell model, and we have a Kelvin model, and those can describe the behavior of a simple behavior of an extension, for example, uniaxial test, or they can be assembled in series or parallel, where these are mechanical elements similar to what we studied in physics, mass, spring, dashpot, friction. These are the elements that we use to represent mechanical behavior, and that's why they're called rheological models. Relationship between stress and strain and time, or in other words, between force, displacement, and time. The next subject is thermoelasticity, and thermoelasticity can result, the thermal stress can result from thermal expansion mismatch between different components, or as a result of constraint, and this constraint can be self-constrained. The material cannot constrain itself. For example, if you have a temperature gradient, the top is going to be hot, the bottom is going to be cold, and the top wants to expand, but it cannot because the lower part of the material is cold and is catching onto it. So it can cause compression on the top and tension in the bottom. So this is an example of self-constraint, and we will study the thermoelasticity of simple subjects like rods, bending, beams, and also axisymmetric systems, such as disks and cylinders, and conclude that with a finite element formulation where we will make our own code and use it for design applications. The next chapter is multi-physics, and in multi-physics we will learn how to effectively run COMSOL. COMSOL is a software that we will use in the course, and it allows us to do couple simulations between fluids, thermal response, heat transfer, in other words, and also the mechanical response, which is structures. So we have like 3 different things going on, and we will use that in our design for the project. So we will learn a lot more about boundary conditions, about meshing, and about the type of simulation that we should be using in heat transfer and in flow and in structures. The next topic is multi-axial plasticity in mechanical design, and that we will start it with something that's familiar with you, such as the yield phenomenon, like Tresca and von Mises. We studied that in strength of materials, but then we will go a little bit beyond to define the yield surface and the theories that are used for multi-axial distribution of the plastic strain. And the next topic is viscoplasticity and creep damage, and there we will study one case that is easy to represent, and that is a pressurized tube, and because this is very critical for many high temperature applications, and the tube is undergoing creep deformation to increase its diameter and also to increase the length if it is a closed tube, and can cause softening of the material. And the last chapter is going to be on fracture mechanics, where we study the Griffith criterion, the stress field of mode 1 cracks, and also define mode 2 or mode 3, linear elastic fracture mechanics, and the J integral in design applications. So these are all going to be included in the class, and as you can see here that the class is going to give us information that will be useful for our design application. So here I show you the topics, and you can find this on the website where we have basically the lectures, and lecture 1 for week 0, which is the first week. And then week 1 has 2 lectures, and 2 has 2 lectures, and so on. And the titles are shown here. For example, in week 2, we have 2 lectures on the rheological models of mechanical behavior. For week 3, we have thermoelasticity. For week 4, we start working on multi-physics simulations using finite elements, and so on. The midterm is roughly the last lecture of the week 5 or the beginning of week 10, depending on whether you're on campus or you are taking it online. So this gives you an idea about the structure of the course. Now I discuss the main component of the course, which is the design project. We used to have the design project be selected according to the student team. You go out and then you find a problem that would be interesting to you, or you're working on it in the industry or research. You form a team and you come back and you give a proposal, and then you start working on it. However, That turned out to take quite a bit of time, and therefore we now focus on one particular project that embodies all of the material that we'll cover in the class. And that is the design of high temperature heat exchangers, HTHX. And those are operating above 500 degrees centigrade. So there's a statement here that I put on the website, and the statement tells us what kind of design constraints we have. So we would like to design heat exchangers for applications in turbine engines, aerospace, hydrogen production, and so on. So these kinds of applications require temperatures that are really high, above 800 degrees centigrade, for example. Not so many materials can work in that temperature range. Not only that, but they require also very high pressure on the order of 80 bars. So 80 bars is like 8 megapascal pressure for one of the streams of the heat exchanger. So we would like you to select an application, and the applications include electricity generation, nuclear reactors, transportation, petrochemical plants, waste heat energy, and hybrid aviation, where we have electric production from a combined Brayton cycle, for example. So these are the applications. Choose an application, and then you find that as the temperature becomes very high, then the strength is lower, and that limits the kind of the materials that you would like to use. You find that you have to use it in a particular way in power cycles, and one of the power cycles that we're interested in is the Brayton cycle, where it has two constant pressure stages and two constant entropy stages, isentropic stages. And it is used extensively in, let's say, jet engines or turbines, where we can define or find equations for the efficiency of that cycle. So the design constraint is that we would use the announcement by ARPA-E, which was launched in last year. So this is a recent announcement where they defined for us the requirements for this ultra high temperature heat exchanger. So we'll take it as a challenge, and then we will do the design where the temperatures exceed 800 degrees C and 80 bars, which is 1100 psi. That's pretty high. And we want to develop new topology, like different configuration. And we want to show that the design product, which is heat exchanger, can actually survive 100,000 hours or more. So these are spelled out, and therefore we want to have you start working together this week as soon as possible to form a group of 2 to 3 students as a team. And then I have on the website in the first week practice examples for COMSOL, which is the multiphysics software that we will be using. So please go to my website, and you will see the 4 different videos showing you how to use COMSOL. And then you can also run an example for the design of a heat exchanger with COMSOL that allows you to become a little bit more familiar with the process. Now once you've done that, you build your own design that can satisfy these criteria. And one of the challenges, as you will see, that the new trend is to use additive manufacturing, because some of the intricate parts of the heat exchanger may not be possible to weld or to drill or to form easily. and that can affect failure, and therefore there's a push towards using additive manufacturing. So if you are interested, you can go into the direction of additive manufacturing and see if that can also give us some benefits in the design. The idea is that, as I mentioned, we wanted to focus on what's called a recuperator, and a recuperator is based on closed supercritical CO2 Brayton cycle. You don't have to use CO2, but if you use a different application, but if you want to follow the guidelines, then we can all stick to the CO2 as one of the working fluids. So the contents of the project is that first we want to describe the Brayton thermal cycle and analyze it so that you'll be familiar with it. And then you do a MATLAB preliminary design calculations by hand, following the equations that are in the manual. I have a manual that I'll show in a minute. And then you do multi-physics simulations after the initial preliminary stage of design. And then you analyze the failure modes due to the three topics that we mentioned in the course: plasticity, and then time-dependent phenomena like fatigue and creep, and then finally fracture. And as you come towards the end of the course, then your objective would be to define a few geometric parameters that you will vary to optimize your design and achieve the effectiveness that is required. We would like to have an effectiveness for this design of 80% or greater. Very, very challenging. So the next step will be failure analysis once we have done the multi-physics simulations, where we use codes that are developed by the American Society of Mechanical Engineers to determine whether the component will fail or not, and also to give us a lifetime for the component based on creep and fatigue type deformation. Finally, the project is going to be put together in a report. We have a template for the report online that you can download, and your report will be somewhere between 20 and 25 pages and is due at the end of the 10th week. We also can use the same template to write a preliminary report once you form your team and came up with a preliminary design, and that is due to at the end of the 4th week as a progress report. So the progress report is worth 25% of the grade of the overall grade of the report of the project, and the final report is worth 70% of the overall project grade. I have a timeline here that you could see for the project. For week 1 is installation of the software and group meetings and the definition of thermomechanical loading constraints. Week 2, material selection, preliminary 2D sketches and 3D solid models using SolidWorks. And then you begin fluid flow and heat transfer modeling and some preliminary stress analysis code calculations. Week 3 is you do the full 3D solid model. So it's pretty fast once you get to that stage, and you prepare a preliminary design report, and then you can submit it at the end of week 4. And then you go to week 4, you couple elastic, thermal, and mechanical stress, and then you start assessing failure as we have in the course. Of course, the course is going to be progressing, and then you'll be learning about the failure due to plastic deformation, due to fatigue, due to creep, and due to fracture, and that will fill in week 4 and 5, and so on. So week 5, optimization, and then we will start now going a little bit deeper beyond the elastic limit. So we do elastoplasticity in week 6, and then we look at what happens when you have on and off situations for the heat exchanger, because under on and off, basically the stresses will change drastically, and you can accumulate fatigue, thermomechanical fatigue failure. And week 7 and 8, we will assess creep deformation and fracture failure criteria. And finally, in 9 and 10, we will do the optimization, finalize the report, and prepare the final product, which is our report that we will submit online. So that gives you an idea about what the project is about. In order for us to implement the project, we'll need software. And the software, I have activated it online. So we have a numerical computing software, that's MATLAB. We have a CAD software, that is SolidWorks. And we have finite element software. And I activated both COMSOL and Abacus. Abacus is optional for those of you who want to get more experience, but we will do most of our work with COMSOL. So what you have to do this week is you have to establish a CSNet account, and by clicking here, and the account takes about a day to activate. Once you have your account, then you will remotely connect to the CSNet server, and once you connect, as you can see here, you authenticate your account, and then you can start using these 4 types of software that we recommend. As I said, I have various issues, various videos that I put online, and these videos will prepare you to learn a little bit of simulations from COMSOL. We also have additional material that in the form of a manual for the project, and we will describe this manual in detail in another lecture. So with that, I'm going to stop here, and hopefully you will enjoy the course and proceed with confidence throughout. Thank you for watching. And